Okay, well, so good morning again, and today we're actually going to get started into the textbook. We have a couple of days to cover Chapter 2. A fair amount of Chapter 2, conceptually at least, is going to be review from General Chemistry 1 when we discuss structure of the atom. But now we are going to be bridging from that General Chemistry 1 understanding to the most in-depth understanding that you will get in PChem next semester for most of you. We'll go into PChem 1, all right? And again, moving this course in front of PChem allows us to make that transition because you spend a lot of time in PChem looking at electronic structure of atoms and trying to understand the modern model of the atom. So we're going to get a view of that in this chapter today. So a lot of our work with understanding the atom, and in particular the hydrogen atom, right? It was hydrogen that was figured out first, and then the other atoms sort of came after that, a little bit later. The understanding came after that. So the big gains in understanding the hydrogen atom came from light, right? And so light, we know, is emitted from excited atoms. All right? And hydrogen was really the first example of this. Seeing this. And hopefully you've had a chance to see an atomic emission or gas discharge tube. We have several of them around here. If you've never seen one, it's a neon light for all intents and purposes. We run some electricity into it, and it glows a signature color. Every element has a signature color that it produces. But hydrogen was really the first gas that this was witnessed for, and that we were able to mathematically model the colors that were observed. So now to the human eye, we see one band of color. You can imagine this being some light emitted from the source over here. And then that light, if it is diffracted, a prism is the easy way to diffract light. In an actual physics experiment, you would use a diffraction grating rather than a crystal prism. All right, a little more, and you have a little more control over the spread of the wavelengths. But if this is a hydrogen source, what was observed were 4 discrete lines of color were produced. Okay, not a complete rainbow. A complete rainbow would be what we term a continuous spectrum. If you have all your colors present and they blend seamlessly from one to the next, you can't really tell where the red ends, where the orange begins, where the yellow begins, okay? It's like a real tough judgment call. This spectrum up here is what we would call a discrete spectrum, or a more practical term, a line spectrum. So line spectrum applies here because you would see individual lines of color, but you always want to remember the word discrete means individually defined things. All right? So when you see discrete values, all right, if it's talking about in a math class, if it's in any of your other chemistry classes, don't let that word throw you for a loop. It just means individual single values rather than all possible values, okay, being available, okay. So that's all that discrete really means for you. So on the one hand, it's like, wow, okay, well that's neat. That's something cool to look at. But the real question is, well, why? Why are only 4 colors produced? In other words, what is it about the atom that allows only these four colors to be emitted? Okay. So we witnessed this, and now we have to sort of think backwards. These colors are coming from atoms. What must be the structure or the arrangement of the atom that is allowing just four colors to come out rather than all colors? And for hydrogen, it's always the same four colors. And if you started to put other gases into this experiment, they would produce different colors, their signature set of colors. All right? So every element was having these discrete spectra, and it must be, we concluded, tied to the electronic structure, because it's the electrons that are gaining the energy when you excite them. Okay? So the proposed idea was that the atom has defined energy levels for the electron. Okay? Rather than the electron can have any energy possible, continuous spectrum, okay, the only way to get discrete values of energy coming out of the atom are if the electrons have discrete defined energies to begin with. Right? If the electrons could have any energy they wanted, then any energy could come out of the atom, any color. Color, energy, synonymous, right? Because a color corresponds to a wavelength, to a frequency, and thus to an energy. Okay? And so this was first modeled by, I believe, I just want to give credit to the first person. Balmer was the first person to produce, for the visible light, that the energy is equal to a constant, which was called the Rydberg constant, times 1 over 1 over 2 squared minus 1 over n squared, or n final now we denote it. So n final was a number greater than 2. Now this was what was called the Balmer series. The visible colors, the 4 visible colors of light that would be produced. This value RH is 2.179 times 10 to the negative 18 joules. It's R. Okay. Once equipment and instruments were developed that allowed us to see outside of the visible spectrum, question?
That's 1 over, is that 1 over z squared or 2?
This is a 2, thank you. Yep, that's a 2, and then, yeah, and that's an n, yeah. So, and I'm about to get rid of that 2 in a second, so your question is very timely, all right? This modeled the 4 visible lines. So if you plugged in 3 here, for example, all right, and calculated out an energy, that energy would be one of these 4 lines. And then if you plugged in 4, you'd get the other line, then 5, and then 6, okay? So you'd predict these 4 lines of color. So this was all working with, again, visible colors, things that our eye can see. But as you probably know by now, the electromagnetic spectrum is much broader than that really narrow band that the human eye can see. So we needed equipment or instruments that could see beyond what the human eye can detect. And once we were able to start working with infrared and ultraviolet, the regions of the spectrum closest to the way the human eye works, or what the human eye sees, all right? So they were really the first that we were able to visualize, okay? We saw that there were additional sets of lines coming out of the hydrogen atom. But they're invisible to you and I looking at them unless we look through an infrared filter or some kind of UV visualizing tool, all right? So once we learned about that, okay, so once UV and IR light could be seen, let's say, by instruments, this equation was adapted. So it became a little broader. The energy was still RH, but now 1 over n final squared minus 1 over n initial squared. And I think I need to go back up here. Sorry. This NF should be an NI. Yeah, where the electron started. Okay. And so this now allowed for what we figured out was going on here was that the atom had energy levels for its electrons. Okay. So this was the proposed energies that an electron could have in the hydrogen atom. And it's kind of like a person being in an elevator in a building, right? You rely on the elevator working, and it's going to put you on one of these floors. It's not going to stop in between. It's not if it's functioning correctly, right? You don't want that to happen. And so the proposal for the structure of the hydrogen atom that supported all of the experimental observations that we'd seen to date, right? This made sense, in other words, that the electron has discrete energies, okay, and it can transition between these different energy levels that we have, all right? Now, what do you notice about the way I drew this sort of ladder of energy levels?
They're separated. They get closer and closer as you get higher and higher.
Right. The gaps are not the same. I didn't make the same distance between each of these. And that is a function of this 1 over n squared that we see in the formula here that's predicting the energies. All right. And so the energy levels we see get closer and closer together as we get further from the nucleus. The nucleus would be down here, be off the board, down here. Okay? So as we get close or further from the nucleus. All right. The Balmer series were the transitions that always ended at energy level 2. All right. And so this is the Balmer series, and that's why in the first equation the 2 shows up. Okay. But if you now allow your electron to go all the way down to the first energy level, you're going to have more lines in this series, okay? And they are going to be of greater energy. Okay? Let's see what you remember about the electromagnetic spectrum, okay? In the electromagnetic spectrum, okay, we have this little wedge of visible light, okay, and then on either sides of it we have the IR, and then we have the UV. Right? Visible really is that small, okay. Relatively speaking, which is higher in energy? Which is the highest energy of these 3 sections? You remember? UV is the highest energy. Okay? All right? And so there are larger energy gaps here, right? You just see it, right? The arrows are longer, right? More energy is coming out. So this is going to be the UV series. Right? There's a name for it, But we don't need to worry so much about even like the Balmer series, right? I'm just more interested in the energies, which is the most energetic, which is the least energetic. Okay? So infrared light has less energy. So this is the energy is increasing as we go that way on the electromagnetic spectrum. If our transitions stopped at energy level 3, there are fewer of them now, right? Because you're cutting off a couple of these transitions here. And there are smaller in energy. So this is the IR series that you'd have. Okay. And again, the human eye wasn't able to originally detect those, but once we had sort of instruments that could see into these regions of the spectrum, we saw these extra lines of color, and the model still worked as long as this number was changed from 2 to 1 for the UVs, or 3 for the IR ones we have there. Okay. Any questions about any of that so far? Yeah.
Are there any bands that stop at energy level 4 or 5?
I'm not familiar with a name for any of those series. Let's see here. They just point out in our textbook, the series that end at 1, 2, and 3. I think that those gaps might be small enough now, stopping from 5 to 4 and 6 to 4. You'd be well down into below the IR portion of the spectrum into, so now you're getting into like, is that microwaves and that sort of thing. So that's where you'd have to look for them. There may be some emission there. Mathematically, it would seem to be allowed. Whether we observe it, though, I guess that's a different story. All right, let's use this equation real quick to refresh our memories. All right, let's find the wavelength. That's lambda wavelength, right? Find the lambda of the line produced when an electron falls from n equals 5 to n equals 2 in a hydrogen atom. So one of these lines on our spectrum here that we drew, it's going to be in the Balmer series, we know already. All right, so we want to figure out what's the wavelength of this energy that's released corresponding to this transition. Now, I've asked about the wavelength. Our equation's all about energy. So the roadmap here, we have to think about the connections. We can use the n values to get the energy that's emitted, and then we have to remember some equations from basic study of light back in general chemistry that relate energy to frequency and then wavelength using the speed of light. All right, so I'll reintroduce those in a second. But first, let's figure out the energy of this transition. It's going to be the Rydberg constant, as this is called, RH times 1 over n final squared minus 1 over n initial squared. All right. So that is the 2.179 times 10 to the negative 18 joules times 1 over 2 squared minus 1 over 5 squared. So break out the calculators today. I get 4.5759, so we can go with 4.58 times 10 to the negative 19 joules. Now, there is some issue. We should stop for a second and talk about direction. All right? We've all know about positive and negative numbers. In this question, I talked about the electron falling from 5 down to 2. And so we want to be thinking about the direction. If an electron falls from 5 down to 2, the energy comes out of the atom. From the atom's perspective, then, energy is lost And so technically, from the atom's perspective, this energy should have a negative sign on it. All right? And so sometimes this formula actually does have a negative sign out in front of it, as it turns out. I'm looking for different versions of it in our book, but you can do with or without the negative sign as long as you think about the context of what's happening. All right? And I prefer to do it that way. On the other hand, we could be looking at our electron going from 5 up to 2. Right? So this is now energy that has to come into the atom, so it's going to be a positive energy. Right? So the sign is it's important only in the context of understanding which way the energy is interacting with the atom, coming in or going out. All right? The wavelength is going to be the same, regardless. Right? It's just, again, whether that's coming in or whether it's going out. But it's the exact same wavelength that we're going to reach. So even if we did associate a negative sign with this energy right now, because it's emitted, we would then take the absolute value of that to go on to the second part where we calculate the wavelength, because there's no such thing as a negative wavelength. All lengths are positive, right? All wavelengths are positive. Okay? So you just want to make sure you don't put down crazy answers with negative signs for frequencies and wavelengths and things. Okay? All right. But energy can be negative because it's got two directions, either in or out. So that's the energy. Now this would be the energy of a single electron's transition. All right. So what's the wavelength of that? So there's two equations that we need to refresh our memory on. E equals h nu. This is the Greek letter nu here. All right. It's the symbol for frequency. We also know that the speed of light ties the wavelength and frequency together. So we could do two separate calculations, or we could smush these two equations together real quickly here, because the frequency would be c divided by lambda. So we could just put that into here and say the energy is equal to hc divided by lambda then, which would allow us to solve for lambda. We'd be swapping the lambda and the e, multiplying lambda to the left, dividing e to the right. H is Planck's constant, which is 6.626 times 10 to the negative 34. It has units of joules times seconds. So 6.626 times 10 to the negative 34 joule seconds. C, the speed of light, has a value of, usually we round it to 3 times 10 to the 8th, but we can get more sig figs, 2.998 times 10 to the 8 meters per second. Okay. And then this is divided by our 4.58 times 10 to the negative 19 joules. All right. Joules are going to reduce. Seconds have reduced. You see that we're going to be left with meters as the only unit that persists, right? And so it sticks around. So 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8th divided by our previous answer is 4.34 times 10 to the negative 7 meters. Visible light, this is in the visible spectrum. They're in that 10 to the negative 7 range, which often gets converted over 10 to the negative 9. So this would be 434 nanometers is what that wavelength would be. If you make the power of 10 smaller, taking it down to 10 to the negative 9, which is one of the sort of, we have these stopping points for milli, micro, nano, pico, that sort of thing. Okay? So that's why I chose 10 to the negative 9. So if you go down to 10 to the negative 9, you have to make the number bigger. They have to go in opposite directions, all right, when you do those shifts. So I made it 2 powers smaller in the power of 10, so the actual number had to be 2 bigger. That's why it became 434 nanometers. Okay? And so this is going to be, if I remember correctly, the low end of the spectrum. So this is going to be like the bluish colored line in the hydrogen spectrum. All right? There would be one line with the 6 to 5 would be even more energetic, so it would be lower in wavelength. So it would be the violet-y purple color. Sometimes it's hard for people to see. And, again, that's the nature of the human eye. Some people look at the hydrogen spectrum and they only see 3 of the lines. Okay, just like we hear sounds slightly differently. Okay, and so that's where now we know the significance of being able to visualize things instrumentally, and we take away that arbitrary ability of the human detection and sensors that we have, our eyes and our ears. Okay. All right. Of course, this can all go backwards. We can solve for, if we measure one of the wavelengths coming out, we could work this problem backwards. We could start with a wavelength, use it to calculate the energy being emitted from a light, and then use that energy to solve for either where the electron started or ended. So that's a different version of this same problem that we just did. Okay, you're just solving for a different piece of that puzzle. Okay, all right. So the next big advance, people were really excited about, studying light and getting a little better understanding about the atom. The word that started to be really popular when this happened was, we're looking at a little section of this here, but the model actually said that these weren't, that these were circular orbits like that, okay, and that those orbits got closer and closer together, like the planets. All right, so the original model and the evidence seemed to suggest that the electron was orbiting the atom, all right, and that it had to do that so that it didn't get sucked into the nucleus. Just like if the Earth all of a sudden lost its linear momentum, wanting to fly out into space, we would be on a one-way course for the sun, all right? And what keeps us in orbit around the sun is this constant pull from the sun, balanced by our desire, the planet's desire, to go in a direction perpendicular to that. And those two constantly pull, and the resulting vector is a circle. It ends up being a circle. So that, that had been well understood and modeled, all right, by this time in the late 1800s, early 1900s, when this was developed. And so the idea became, that must be what the electron is doing, because it's negatively charged, the nucleus is positively charged. Why doesn't it just go right in? Because it's like the planet, all right? And so there's this vector in this direction and a vector in this direction, and they result in these orbits, okay? But it became increasingly clear that electrons didn't play by the same rules that a planet does, or that any object, and for that matter, in the real world obeys, all right? And an entirely new system, known now as quantum mechanics, was developed to help us understand the behaviors of subatomic particles. So there's different realities for particles that are this tiny, in our world. And some people get lost in the philosophies of all this. It's really good stuff to sort of explore the concept. Some people get lost in the mathematics, all right? Been various times in my life when it's been very challenging to complete the mathematical components associated with quantum mechanics, all right? But it's nevertheless a really, really important concept as a chemist to understand the structure of atoms. And nowadays, the stuff that Dr. Forsman is going to start to have you do in P-Chem is all based on quantum mechanics, and we can save a lot of time and a lot of money and a lot of effort by modeling things, by predicting how things are going to behave, before we even, like I said, spend money on trying to make a reaction happen or make a chemical or get it to do something in a chemical reaction. None of that's possible without the principles of quantum mechanics. All right? Otherwise, we would just all be trial and error, okay? Which is not the safest of policies to have, to be honest. Okay? So the real origins of quantum mechanics briefly are described in Chapter 2 here. One of the highlights that bridges from studying atoms over to quantum mechanics is a few scientists who invested a lot of their efforts into explaining what's called wave theory and treating the electron not as a particle, but rather as a wave, as a standing wave. Okay? And there exists now what we call wave-particle duality. Everything has both a particle nature and a wave nature. Your particle nature is what we're most used to seeing in our everyday lives. You can see me, you can locate me, you can use Newtonian physics to understand my motion and where I'll be. If I jump up, you can predict how high I'll go and where I'll come back down and how long it takes. Okay? That's all particle nature. All right? But at the same time, I'm actually producing a wavelength, just like these lights right now, or this hydrogen atom when we charge it up. All right? Whenever I'm moving, I'm producing a wavelength, but it's impossible to see because of how big I am. All right? And even any object that has a mass that's significant enough that we can measure it in the lab produces an insignificant wavelength that can't be detected. It's not until we get down to subatomic particles, things that we can't weigh, when the rules change and then the scales tip and the wave nature wins out. And then we can't actually see an electron like you see me now. And so it's weird, right? That's this philosophical difference of the two worlds, the quantum mechanical world versus the real physical world that we're in. Okay? So it reaches a point when things get small enough that you now wouldn't look at the particle, you would see the light that it's producing instead. And that's how you're understanding that thing. And that's what's called the wave nature. Okay? So there was a push to try to use the wave concepts to understand the electrons. And it became increasingly clear that electrons weren't actually on these orbitals, these orbits, I should say. That it was impossible for us, if they were on an orbit, so here's the logic. If they were on an orbit, shouldn't we be able to figure out where they are? Just like a planet. We know the Earth's orbit, so if we weren't on the Earth, we should be able to see where the Earth is and to predict where it is. Okay? But nobody was able to do that. And so it's like, what's going on, right? And that's where this shift in realities occurred, all right? And it became more and more clear that there was some connection between being able to interact to see an electron, and then that actually changed where the electron's at. All right? And it's a neat little principle. To see an electron, what has to happen? Light has to bounce off of that electron and come to your eye. You see me right now because light bounces off me and comes to your eye. When light bounces off an electron, what happens to the electron? Whoop, it just changed where it's at. You just change its energy because light is energy. And that's going to move the electron. All right? And so there was Heisenberg introduced a real famous relationship called the uncertainty principle that says, sorry, but there's just a certain amount of uncertainty in either the energy or the location, position of an electron. Okay? And so the more accurately you know the energy, the less accurately you have to accept that you're going to know the position or relative location of the electron. Okay? Not that we should give up on pinpointing where the electron is, outside of the atom, but we're not going to get an exact position, is I guess what we should settle for. Okay? Can we do better than, okay, just knowing nothing though? And so the concept of orbits were replaced by orbitals. Orbitals became the term to describe regions of space rather than a specific ring or a specific position. Orbitals, remember, are regions of space in an atom. And originally it would have been hydrogen, but now we know they're in all atoms. So they're regions of space in an atom that have higher probability of containing an electron than other spaces. Just like I could look at your college right now, there are some spaces that have a higher likelihood of students being right now, and some spaces that have a less likelihood of students being right now. Okay? So you can think of classrooms as being like orbitals. There's a pretty good chance that there are students in classrooms right now. It's not a guarantee, all right, but that's what the odds tell us. Okay? So we're kind of playing the odds right now with these hydrogen atoms. Okay? These orbitals are described by what are known as, or are predicted. Sorry, they're not described. They're predicted by the equations that model an electron as a wave. Okay? Those equations are called, for that reason, the wave equations. All right? The symbol for a wave equation is the Greek letter psi, psi. Okay? The math that you'll do in PChem is described. It's described in 2 pages here in our textbook, and it's like chapters in PChem, right? So that shows you the difference. Okay. But the math that you're going to do in PChem says that if we operate, okay, you've all had some math, so I hope you understand what the term operate means. That performs some function, you do something to an equation, right? So if we operate on an electron's wave equation, sometimes also called its wave function, but it's wave equation, okay, with the operator known as the Hamiltonian. Okay? So there's tons of operators. Square root, that's an operator. Squared, that's an operator, right? So, and then this is a special operator. It's called the Hamiltonian, all right? If we use this Hamiltonian operator on one of the wave equations, the result is the energy of the electron. Okay. Okay, now, again, trying to keep things lower mathematical, right? Mathematically, this would look like H psi, that's when you operate, oftentimes there's a little hat over the operator, equals E psi. Okay? So when you operate on the wave function, the result is the energy actually multiplied by the wave function again. This is a special property of wave functions of electrons. It means they're what we call eigenfunctions and eigenvalues. The E would be what's called the eigenvalue. This isn't true for every function. If I take the square root of some equation, the answer is not a number times the equation again. It's not, okay? This special operator when you use it and you apply it to the equation, you get the equation back, now multiplied by a number, another constant up front. And so that makes, we use the term eigenfunction to describe this special situation and this scenario. So wave functions for the hydrogen atom are eigenvalues or eigenfunctions of the Hamiltonian operator. Okay, that's true. It seems to have a hard time finding me when I come over here to this side. So, all right. Anyway, what is this Hamiltonian? All right, let me show it to you. There's several different versions of it. Okay, but the simplest way to express the Hamiltonian is that it is negative, a couple of constants here, h squared over 8 pi squared mass, okay, times the second derivative of the wave function. Okay. Now this is the Hamiltonian in one dimension. A hydrogen atom is not one-dimensional, though, right? It's three-dimensional. So there's going to actually be, for the full treatment of the hydrogen atom, there's going to be 3 partial second derivatives. One for x, one for y, one for z. But let's not worry about all that for right now. Okay? You can do it for one dimension. You can do it for the others. Okay? So we can just look at it for one dimension to keep life simple for right now. Okay? And so when you... since I have psi in here, by the way, let me go back and make that a little more accurate. This is h operating on psi, so the second derivative is part of it there. Okay? And when you do this, you get back, like I said, energy. So all of this ends up, when you take the second derivative, that's how you get back to your original function. So, what kinds of functions could exist that actually do this? What kinds of functions, when we take their derivative or their second derivative, return the original function? Right? Like an x squared, when you take its derivative, it becomes just x. Right? Or an x cubed, when you take its derivative, it becomes x squared. Right? So what kinds of functions, when you take their derivatives or second derivatives maybe, come back to themselves? Exponentials do that? Okay, yep, that's good. What's that? That's exponential, yeah. There's another important one. Anybody? Trigonometric functions. Sines and cosines, right? Not the first derivative. First derivative of a sine becomes a cosine. But then when you take the derivative of that, it turns back into a sine function again, right? And actually they're related. Exponentials and sines and cosines, they're related, right? If you have an e to an I, it becomes an exponential. So, that's the math that we don't like, all right? But so essentially they're the same thing. But usually we use the sine and cosine versions of them, okay? So that's what I wanted to get at with this right here. We're not going to do too much of it or anything. So the types of equations that can satisfy this include sine and cosine functions. That's because their derivatives and second derivatives will come back to being sines and cosines. Right? And what you'll be doing in physical chemistry is learning a lot about these wave functions and how we can construct them for an atom and what the criteria are that we have to use. And so you're going to learn a series of representative cases, all right, The first one is what's called the particle in a box. It's described briefly in our text here for you. All right, you could look at it. It's not too bad. And then you start to consider rotation. All right, and so you have the rigid rotor, and then there's the simple harmonic oscillator, and those rely on some physics concepts, which is why you've got to have taken your physics, or ideally before you get to your P-Chem. All right, but I don't want to get to dabble in too much of that because it would take us, honestly, a couple of days of studying that. Okay? The real important piece, though, is that these wave functions, and then this will start to return to stuff that you have heard of before. So not only do these wave functions have sines and cosines in them, but it turns out that they have sort of these magic numbers, all right, which we call the quantum numbers as well. Okay? So every wave function or wave equation also contains a group of three. They're not constants, but they're for a given energy they are constants. So they're a group of three numbers that are related to the electron's energy, location, or position, let's say, and orientation in space. And I don't mean outer space, right, when I say that. I just mean in space, right, in the space outside of the nucleus. Okay? These three numbers are known as the quantum numbers. N is the principal quantum number. It defines the energy. It is the same N that we saw intentionally. They ended up using that, right? When they realized there was a quantum number related to energy, they used the same designation as had been used in the Rydberg equation earlier. Okay? So there's what energy level the electron is in. Okay? But it has a secondary role. This also defines the size of the orbital. So how big the orbital is. The larger n is, the bigger the region of space that electron is likely to be in. Okay? And so we have some smaller classrooms and we have some bigger classrooms, right, in our areas on campus that we have. And so there's a system in the atomic structure that the first number is telling you roughly how big that classroom is. Okay? All right. The second quantum number, L, is called the angular momentum quantum number. All right? And it defines the shape of the orbital. Okay? And then the third quantum number is the magnetic quantum number, and it defines or describes the orientation of the orbital. Okay. Our classroom's window is pointing roughly, let's see which way, it's pointing roughly, one direction, north-south. Let's see, that's the front of campus, and then our window's pointing north, yeah, okay? So it's kind of like saying that, which direction is this orbital pointing at, or, in space, okay? All right. And so these three numbers are contained as, they look like constants in the wave equation if you're actually seeing the wave equation. But they're what we're really trying to pull out so that we understand where that electron is that's described by that equation. Okay. We learned about these quantum numbers back in your first year, first semester classes. So there's some rules about these numbers. N must be an integer whose value begins with 1 and goes up from there, right? So N must be an integer. Your elevator can't stop at floor 5.2, right? The elevator has to stop at 5 or at 6, all right? So that's the first rule for N. The value of L, or values of L, first of all, we want to say we want to know that it depends on the N of the electron. So the N has to be defined. Once the N is defined, L equals 0, 1, 2, up to a maximum of N minus 1. Okay? So there is a range, but L will be one value in this range, or this set of options. Okay? The higher N is, the more options there are, but ultimately the function has only one of those options. It's only using one of those options for the electron. And that's what kind of confuses people sometimes. We talk about list out all of the L values. Ultimately, the electron has just a single one of those values, but we want to acknowledge or figure out what the possibilities are. Okay? And then M sub L also depends on L. Depends on the value of L of the electron. So once the L is defined, M sub L is again a range. It reaches from negative L up to 0 up to positive L. Again, that's going to be a range, but the electron has one value of M sub L in this range. There is a fourth quantum number, unassociated really with the electron's position in space. It's what's now known as the spin quantum number, M sub s. But we don't need that one right now to understand where electrons are. Okay? All right, so let's do just a couple of little examples. So for example, if n equals 3. So if an electron is in the third energy level, okay, what can we say? This electron can have L equal to 0, 1, or 2. Those would be the possibilities. If L equals 0, then M sub L could only equal 0 as well. All right? Because you'd have to go from negative the value of L 0 to positive the value of L 0. So it's just 0. Okay? If, on the other hand, though, if L equaled 1, then M sub L could equal negative 1, 0, or positive 1. Any one of these three would be a possible, legitimate M sub L value that the electron could have. If L equaled 2, then the electron could have M sub L value negative 2, negative 1, 0, 1, or 2. Any one of those 5 possibilities that we have there. Okay? All right. So that's an example of how they work. So ultimately, we would have some options, but the electron would be 3, and then we'd be in one of these 3 categories here, and once we pick one of those, we'd come over and be picking one of these. Okay? All right. Now some general language that we use, okay, for the L quantum number. For the L values, L equals 0, we generally describe this as an S, what we call subshell / orbital. It does double duty because L can be describing a group of orbitals, okay? Or you could be talking about the ultimately one orbital in that group. So we call it the S subshell or the S and S orbital. If L equals 1, that's what we call the P subshell. When L equals 2, that's our D. And L equals 3 is an F. Oops, sorry, I wrote the wrong thing there. S, P, D, and F, right? You've heard of these before. Okay. Those are the only ones that we use numbers or letters for. Everything else we stick with the numbers. Now you may remember, back again from your Chem 1 class, or maybe you've seen it since then, some pictures of these orbitals. And we try to draw sort of what these look like for students to give them an idea. And our book has some of these images as well. All right. So in general, an S orbital is spherical. All right. So if your nucleus was at the heart of a Cartesian coordinate system, an X, Y, Z system, okay. If your nucleus was at the heart of that, your orbital would be in all 3 dimensions, sort of equally spaced like this. Okay. When we draw these pictures, the understanding is that there's a 90% likelihood, I don't want to say chance, okay? So there's a 90% likelihood the electron's in that space, if we're saying. So that's the, again, this is all probability. There are classrooms that are empty right now on campus, okay? And there are students who should be in certain classes, but they're not in those spaces, right, that are set up for them right now, okay? So we're talking about where we're most likely to encounter the electron. So if the wave equation tells us that the electron is in the 1s orbital, this picture that we draw or associate with that 90%, that we've chosen to draw it at a distance that encompasses 90% of the probability. A different way. If you wanted to encompass 100% of the probability, you'd have to go out to infinity. Okay, because there is some chance the electron could be way, way out from the nucleus. All right, and so the pictures have always been sort of just decided you'll encompass 90% of the probability of locating the electron. Now that doesn't mean, this is a different discussion, but it doesn't mean that it's equal 90% anywhere inside that. There are different, and they're really cool, equations or calculations that tell us there's even higher probability within that sort of sphere that we drew there of it being at certain distances from the nucleus. Okay, and the book shows us how to do that. Okay, so the S's are spherical. The P orbitals are generally considered to be dumbbells. That's what we always call them, dumbbells, right? They have sort of 2 lobes to them, okay? The p orbitals like this would be the px, for example, on the x-axis, okay? So we say that this has 2 lobes separated by a. Does anybody know what we call this point between the 2 lobes? Anybody heard of that before? A node. That's right. N-O-D-E. Separated by a node. And since you gave us that name, what is a node in general? If I had asked you to define a node before showing it on the picture there, what's a node? In any waves, it works in physics and stuff too. Do you have it? Visually, I can understand why you're saying a central point, but that's probably not the best way to think about it. Okay? It's not necessarily at the energy zero either. Something else is zero. The probability of finding the electron there is zero. Okay? So that's what these pictures are spaces where the electron could be. Well, it's bupkis right there, right? All right, and that's what's called a node. A node is a position with no or zero probability of the electron being there. Okay. And we can predict where these nodes are from the equations that give us these orbitals and these shapes, actually. All right. So what I want to do now is sort of show you why is the P shaped this way. And to this point, it's probably always just been told to you, here's the S shape, here's the P shape, here's the D shape. Okay. So it's a matter of why is the P orbital shaped like this dumbbell here. Okay. In your text, if you don't have your text, that's fine today. I don't really need you to bring it every day. In your text, there's a table. Let me find it real quickly. There we go. On page 19 of the wave equations. You might look at this later on. I think one of your homework problems has you using one of these. So page 19, there's a table of the wave equations of the hydrogen atom. Okay, hydrogen atom's electron. All right. Let's look at this px. Okay, now in reality, the real psi is broken apart into a radial function, okay, and an angular function that gets called phi a lot of times, okay, like that. So there's a radial piece, which is distance, and then there's an angular piece, which is in what direction are you talking about, right? So if I'm the center of an atom, and I'm like asked about where is the electron, all of a sudden I'm thinking I'm like Professor X in his Cerebro thing, right? He's out there in the middle. It could be anywhere out there, right? And I've got to figure out how far out are we talking. There's a function for that, the radial part. And then in what direction do I need to rotate? And there's actually two angles here, right? I've got to rotate this direction, and then potentially up and down. So there are actually two angles that we'd have to worry about. Okay. And as you've probably seen in some math classes, maybe to your dislike in some cases, all right, you can use Cartesian coordinates, x, y's, and z's, or you can use polar coordinates, r's and thetas and phis, all right? And there's all sorts of ways to do this. And so that's why this table, if you look at this table, that's why it looks so convoluted. You're really just seeing some of the same thing in those different languages. Okay? All right. What I want to do is I'm going to pick the equation for the px. The px, this would be angular wave equation, is 1/2, well, it's not really so much an equation, but it doesn't look like an equation, times the square root of 3 over pi times x over r. Okay. If we set this equal to 0, we can solve for the values or value, in some cases it's multiple, but the value or values of x, in this case, because it's got x in the equation, that will give this function a value of 0. Now what I haven't said yet is that the probability of finding an electron, this whole idea of the probability, is related to the square of the value of the wave function. So if the wave function is 0, what's the square of 0? So what's the probability? See? So we backed our way into understanding where these nodes are going to be. The nodes, the positions where we're not going to find the electron in an atom, all right, are going to be found by setting the wave functions equal to 0. Now, what about the radial part I said over here? So this is the phi part. What about the radial function? It doesn't matter. Since they're multiplied, right? If phi is equal to 0, r times phi is 0. Okay? So we can divide and conquer here. All right? We don't need the more complicated equation. We can just break it apart, set any chunk of it equal to 0, and we've predicted where one of these nodes would be. Might sound complex, but as soon as we start to do it, I think you'll see it's actually not too bad at all. So what do? Set this phi equal to 0. So 1/2 root 3 over pi times x over r equals 0. The only way this can equal 0 is if I'm done. X equals 0. All right? Why? Because 1 over 2 square root of 3 over pi, that's just a number. That can't equal 0. R does not equal 0. R is the size of the atom. It's the radius of the hydrogen atom. It's a constant, in other words. Right? So the only variable in this equation is x. The only way for this equation to equal 0 would be if x equals 0. So what does x equals 0 look like in three-dimensional space? I'd rather draw it up here. Okay. So if this was, I'm going to draw, this is my x-axis, here's my y-axis, and here's my z-axis. What does x equals 0 look like? Does anybody know? What would it be? Just the center? X does equal 0 there. You're right. You're right. But so do y and so do z. Do y and z have to equal 0 according to my equation right there? No. Just x does. So this is one point. Are there any other points where x can equal 0, but maybe y and z don't? In fact, this whole plane of space, right? It's this flat plane. Okay? So this is a plane. X equals 0 describes a plane. So now if we had a sphere before, superimpose that S sphere on here now. But now it can't have any probability at the no, I did that wrong. Sorry, guys. X does not equal 0 there. And that's why it didn't look right. It is a plane, but it's not the x-axis. It's the plane of y and z. This way. All right? It's this vertical plane so that x is always at its 0, all right, on the x-axis here. That then is going to push that circular probability of the s orbital, probability everywhere, it pinches it now. And it says, nope, you can't have any probability on this plane And so the sphere, it's got to come back down into that 0 point from each side. Okay? And it's going to come in. And so it takes what was a sphere, and it's just like a balloon. Twist that balloon at the middle now. Now you could do this in the x direction, you could do it in the y direction, you could do it in the z direction. That's why there are 3 different p orbitals. One of those corresponds to m sub l equaling -1. One corresponds to m sub l equals 0. One corresponds to m sub l equals 1. And we commonly call them px, py, pz. All right? So any of the equations in table on page 19, this table 2.3, can be used to determine the nodes of a wave function, a wave equation. Right? So now that's how we can actually graphically predict them. But we can also draw some conclusions about nodes in general. Okay? Every orbital has, as it turns out, a total of n minus 1 nodes. Okay? So if you know the n value, you can predict the total number of nodes that this orbital has. Okay? There are nodes in the angular functions that we just found here, but there is the possibility of there being nodes in the radial functions as well. Okay? The angular nodes the orbital has, or orbitals have, L angular nodes. So for a p orbital, like we just looked at, for px, L equals 1. And thus we had 1 angular node. All right. And then the radial nodes make up the difference. It's going to be n minus 1, the total nodes, minus L, or it might be easier to write n minus L minus 1. That's how many radial nodes you'll have. The sneaky thing about that is that s orbitals have these radial nodes in them. An s orbital, L equals 0, so it doesn't have any angular nodes, that big sphere. But inside that sphere, if it's a 2s or a 3s, 2s, energy level 2, n is equal to 2. So there are 1 node. But it's not an angular node. 2 minus 0 minus 1, it's a radial node. There's a dead spot inside this sphere, which we don't usually see because of how we visualize the outside of the sphere. But at some distance inside the big sphere, there's another shell, another sphere with 0 probability of the electron being at that. So it's kind of like a seat that, we have this continuum of seats. There's a seat that nobody's ever going to sit in. All right? There's no chance that a student's going to sit at that particular spot, for example. All right? And that would be a radial node, as it turns out. Okay? All right. So that's how far we wanted to get today. Your first homework assignment is posted in Moodle. I don't remember the numbers off the top of my head, so please do look at Moodle. It's several problems out of the Chapter 2 text. All right? Handwritten. Please do try to write neatly for me. All right? If you have scrawl handwriting, which I put myself in that category at times if I'm not paying attention. You can type out, some of the stuff might be written or whatever. If you want to type things out, I'm happy to accept that as well. But if your handwriting becomes tough for me to interpret, it becomes tough for me to grade your work in the class. Right? Have a good rest of the day.